I didn't see the point of a function until I became a teacher. Okay, so I learned it. I learned how to identify a relation as a function. I learned how to work with functions. So I knew what they were. I just had no idea why they were useful. And I didn't care. Right? I knew I could get stuff right on a test, and that's all that mattered as it applied to this. As it turned out, it's actually the most important thing in terms of how you actually use math. Right? So it's just I wasn't actually using math as a student. I only started using it when I became an adult. A function, I mean, you could read through all this stuff, and I'll read it with you. But a function is the idea behind it is predictability. The idea that if you have an input, that you'll get a single output related to that input. All right. So I just kind of equated to the idea that if you were to, I don't know, have an equation that'll tell you how much money you're going to earn over time, you would like that equation to spit out a single answer when you put in a particular value. If I'm talking about how much money I'm going to earn in 10 years and I have an equation, I want that equation to give me a single answer when I plug in the number 10, not give me like 4 or 5 different answers. Because if it gives me 4 or 5 different answers, that's uncertainty. I don't like uncertainty. I want to know where I'm going to be in 10 years. I don't want to know 5 different possibilities of where I could be. Now, if those 5 possibilities are close to one another, then maybe I can live with it. But if they're nowhere near each other, let's say it tells me in 10 years, 5 years, 20 years, whatever, that I could be making $1 million or I could be losing $10,000. That's some wide variation there. I don't like that. Now, if it's a difference between, let's say, 200,000 and 205,000, well, that's not that big of a deal, right? So, I mean, it may, when you get into that territory, it may seem like a big deal, but it's less of a concern than it would be if there was a wider margin, like $1 million versus negative 10,000. All right, so that's a very simple example of why a function would be important. In terms of a graph, if I tell you to graph a point, and I tell you x is this, you'd like to know what y is going to be, right? A single point for y. If I tell you graph this coordinate, and I say the x value is 2, the y value could be 7, 9, 13, 14, or negative 32. Like, whoa, just for that one x value, I have to graph all these y values? That doesn't seem like fun. All right, so the fun factor is also a component. All right, so definitions, so textbook definitions. A relation, set of input and output values represented in ordered pairs. So that's x and y, all right? Relationship between sets of information, all right? So not always in terms of particular variables and numbers. Sometimes it's an idea. You input one thing, you output something else, all right? Maybe it's something vague, like, I don't know, you're taking medicine. You input a dosage, you should output some sort of effect. All right. So if you're taking a medication that's supposed to be a fever reducer, then your input would be the amount of medicine that you take, or maybe how often you take that medicine. The output should be your temperature. All right. Whether you're in the fever territory. All right. So input output, pretty straightforward. All right. So this is really just talking about x against y. All right, so some x coordinate versus some y coordinate. Any comparison of x and y is a relation. All right, so you think about different comparisons between x and y. Well, maybe they could be equal, maybe one's more than the other, maybe one's less than the other. All right, so all sorts of different possibilities. The relationship between eye color and student names. All right. The x would be the eye color, the y would be the student's name. All right, so you have your examples there. Function is a relation that pairs each input with exactly one output. Right, that's what I was talking about before, where you're looking at predictability. You're looking at getting a single outcome when you have a particular input variable. All right, so you could read through that. But the examples there, not okay for a function, 5, 1, 5, 4. All right, and that's because 5 is giving you 2 different y values, whereas 5, 2, 4, 2, that's fine because 5 and 4 are each giving you their own outcome. So they're not giving the same, or you're not getting 2 different outcomes for the same x. All right, so that's what I was talking about before, where if I give you a period of time, let's say 10 years, I would like to know a single outcome for that. All right, let's say my value at the end of 10 years is $100,000. Does that mean that your value at the end of 10 years can't be 100,000? Maybe your value after 1 year is 100,000. Maybe your value after 6 months is 100,000. All right, does this all make sense? Like, people make money at different rates. Like, when I hit 100,000 and when you hit 100,000, maybe at 2 different moments in time. All right, so 2 different x values leading to the same y value, that's not a problem. All right, we can both make $100,000. It just might take us differing amount of times to get there. All right, but if I were to tell you that you, again, at the end of 10, you're going to make 100,000 or 50,000, you're not going to like that because you want to know what. All right, and this crapped out on me, so let me fix it. And there it is. All right, so a little machine analogy. I it's people on the internet have a lot of time on their hands, so they make drawings and cartoons and stuff. Yeah, I don't know. Like, cool. So, if you wanted to know what a cartoon factory would look like in somebody's mind, there you go. All right. Now, domain. Domain is a list of all possible input values. All right. So, and the emphasis is on the all possible part. All possible is like the worst phrase ever, because that means that you have to account for every single possible input value that could exist. All right. We learned when we talked about excluded values 2 units ago, we learned how to state the domain. We just did it indirectly. So what we want to do is identify anything that x cannot be, and then pretty much everything else is going to be what x can be. All right. So be on the lookout for what x cannot be in most cases, and you'll have kind of an avenue to help you figure out what it can be. All right, but in this case, it's pretty simple because we're given a list of all possible x values based on this scenario. We got these colors here. Some are uniquely written and some of them are not. Some of them are repeats. But the domain would be a list of each unique x value. All right, so I got green. I got blue. I got brown. The next one would be blue, but I already have that, so I don't have to write it again. After that would be brown, already got that. And then green, already got that. So close it up. The range would be each unique y value in the ordered pairs. So I got Sally. I got Erie. I got Ben. I got Ava. I got Tony. And I got Poe. You got Tony. All right. Poe Dameron. All right. So, I would want to know, is this example a function? Why not? Well, let's go back to the idea of a function. So, and the example I think does a really good job. Not a function. The same x value leading to two different y values. This is, these are unique. So, do I have the same x value? So here's green and green leading to two different y values. Well, yeah, green gives me Sally, and green gives me Poe. All right, I can't for some reason say that. I don't know why. It's a tongue twister for me. So no, and I'll do it with a little diagram. Green can give Sally, or it could give Poe. All right, that's one example. I could look at, what do we got? Blue. Blue also is Ari or Ava. Brown is either Ben or Tony. All right, so there's a lack of predictability there. The idea behind a function is, can I determine the name of a person based on eye color? I think it was eye color. All right, so can I determine the name of a person based on eye color? If the answer is, in this case, because eye color comes first, and then the name of the person comes after that. So the question would be, can I determine the value of y based on the value of x? If the answer is no, not a function. If the answer is yes, it is a function. All right? So if I were to say, okay, the eye color is green, give me the name of the single person that would be. No, because there's confusion. If it's green, it could be either Sally or Poe. All right? Now, if green was only written once, so green and Sally, then it never came up again, then I could say, yeah, at least for that part of it, I could say it's a function. Right? But not the case. So that's an important question, and that is the distinction between a good answer and a great answer. Right? So what I have in black will get you most of the credit. The way to get full credit, the perfect score, is to really think about what I wrote in red. Right? Can you determine the name of a person based on the eye color? So can I determine the y value based on the value of x? All right. So if I give you an equation, if I give you a graph of a line, and I tell you what the x value is, could you tell me what the y value is? So I give you the graph of a line. Now, I didn't say what kind of line, so let me just draw some arbitrary line. And I have some x value here. Is there a single y value that goes along with that x value? Yeah. I mean, I don't know what it is, but there is a single y that goes along with that x. All right. So what if I made it a horizontal line? That's supposed to be a horizontal line. Is there a single y value that goes along with this x? Yeah. It just happens to be the same y value that would go along with every other x. All right. Now one more. What about this line? I got my x here. Is there a single y value to go along with this x? No, because I could put a y value here, I could put it here, I could put it here, anywhere along this line. any one of those, I mean, there's infinitely many possibilities, right? Here, in the first two cases, a single y to go along with the given x. Here, more than one y to go along with the given x. All right, so this is telling me, I mean, I didn't draw the diagonal line going downward, the one with the negative slope, but it's telling me, just by looking at this, that the only one that I need to be worried about in terms of a linear function, and we've been living in the world of linear functions throughout this entire course so far, the only one I need to worry about would be the vertical line. All right? Everything else is going to be a function. Which brings us to something called the vertical line test. All right, we use that to determine if the graph represents a function. If the vertical line intersects the graph more than once, the graph is not a function. All right, so the example, label a graph as either a function or not a function. Meaning, can I draw a vertical line at any point that I choose, anywhere along the graph, anywhere where the graph exists, and have it intersect more than once? If I put it here, will it intersect more than once? I'll actually draw it, make it a little bit more obvious. No, right? No. Hey, what are you doing? Over here, no. I really got to tap on it every single time. That's aggravating. Trying desperately to find a place where it would intersect more than once. So far, unsuccessfully. Oh, that one moved on me. Yeah. Oh, get out of there. All right, so what do we say about this one? This one would be a function. It's when it intersects more than once that it's not a function. So in the second one, what are we saying? Not a function. Because I could draw it really anywhere. Anywhere where the graph exists, except for that vertex. That's the only place where it'll actually intersect only once. But everywhere else, and all you need is for it to intersect more than once for a single line that you draw. So you're looking for that one counter example. Once you find that, you know that it's not a function. All right. And again, that's because you're getting more than one y for a single value of x. So not a function. All right. So if I place my x here, I could get a y up here, but I could also get a y down here. There's confusion. Which y is it? I'm not able to use the model, whatever this equation is modeling. I'm not able to use it as a predictor. And that's what we want. We want our equations to help us to analyze real world situations. All right, this is not going to help us. All right, what about the last one? Function. Yeah, broken watch is right twice a day. So if I draw a vertical line anywhere here, it's only going to intersect once. Only going to intersect once. What about on the y-axis? Why does that not intersect twice?
Less than or equal to, and one is just less than.
Right. Yeah. This is an open circle showing that there's no point there. This one's actually greater than, but you have the right idea. So less than or equal on this interval, greater than on that interval. There's actually no point there where that open circle is. So I could draw my vertical line right on the y-axis. It's only going to hit the one point that exists. All right. All right. Little practice. Which one of these is a function? Is a function.
2.
2. All right, we talked about it on the previous page. The only type of line that actually is not a function is the vertical line. All right, I kind of look at the vertical line as, it's kind of weird because we use something that is not a function as the test to determine whether other things are functions. All right, so the vertical line is not a function, and so I kind of look at it like, when I'm placing it on another graph, I'm looking for similarity. Basically, if that graph, the graph I'm testing is anything like a vertical line, meaning the y values occur more than once for a particular x, then it's not a function. So I kind of look at it, if I'm the vertical line, and I'm evaluating other functions, I say, okay, other function, if you're anything like me, you're not a function, right? And so here, okay, you're nothing like me. Here, okay, you're kind of like me because you have 2 possible y values. If you have more than that, you're even more like me, all right? But this definitely would pass the vertical line test. This would fail for the same reason the middle example up top would. And same thing with number 4, except it's curved rather than angular. All right, domain and range. And then state whether it's a function. Okay, well, my domain would be a listing of each unique ordered pair. Each x value within the ordered pair. I can't make my squiggly brackets anymore. I've lost it. No, there it is. All right, in increasing order. So what's my smallest unique x value? -2. What's the next one up? 1. After that? 3. Finally? 4. All right. We don't have any, oh, we do have a repeat, but we eliminated it. All right, so the x value is repeating. We have a 1 that occurs twice. Keep that in mind. The range, all unique y values, lowest to highest. What's the lowest? Then a 3?
Yeah.
After that? 5. And finally? 7. All right, so going back to this, we have a 1 occurring twice. That means if I were to graph this, I'd go over 1, up 3 and plot a point, go over 1, down 3, plot a point. All right, so the number 1, the x value of 1, gives us 2 different y values. So is this a function or not a function? Not a function. And that's because 1 corresponds to a 3 or a -3. All right, state the domain and range. State whether it's a function. And again, the explanation is fine. You know, just a little tree diagram. 1 gives us 3, -3. That's good enough explanation for me. But again, that really good explanation goes back to what I was talking about on the previous page. All right, I won't go back to it, but it's basically, can I determine the value of y just by knowing the value of x? All right, if I tell you the number is 1, tell me what y is. You'll be like, well, it could be 3 or -3. Once you throw an or into your answer, it's out. It's not a function. All right. So my domain would be part of the set of A because the arrows are leading away from A into B. So domain would be the set of A. Such that we're looking at the numbers 3, 4, 5, and 6. There's a 7 in there. Thank you. So 3, 4, 5, 6, 7. 3, 4, 5, 6, 7. Yeah. Thank you, thank you. The range would be a set of B such that the values, well, we want them in increasing order. So 1, 2, 3, 8, 9, 12. All right, so the big question, function or not a function?
Yes.
So function. All right. Now I won't draw a diagram to illustrate it. We actually have a diagram here. So a brief explanation instead of a diagram.
Didn't you like do like an opposite diagram saying like 6 like
draw the tree like the opposite way and say like 6, 7, and both going as 12?
Yeah, but they don't have to in order for it to be a function. The only condition is that 6 can't go to 2 or more separate values in B, right? Or not just 6, but anything. So the fact that 12 is corresponding to 2 different values, it's actually just, it occurs, but it's not relevant. All right, so what I would say here is we can determine B just by knowing A. If I know A, then I know B. If-then relationship. There's no doubt about it. I give you an A value, you can definitely tell me what the B value is. So 5. Exactly. Right? It doesn't matter what I choose. Even the cases of 6 and 7. 6, 12. 7, 12. All right? There's no situation where I say 4 and you're like, well, I don't know, is it 1, 2, 3? But it's definitely 0.1, sorry. These are decimals? No, those are just dots. Okay. Why are there dots there? Typo bonus for someone. Get rid of the dots. Dots are, nobody likes dots. I mean, they're all right on the left side.
Maybe Atticus has it.
I mean, I didn't think they were decimals initially, but I did have that moment of pause.